We're going to get through as much as we can today, lesson 91, 92. If we don't get through everything today, we'll pick it up. We'll try to pick it up tomorrow. Now, tomorrow I'm going to be out of the room, so what I'll try to do today is finish out the video with the other class. You guys will work on things in class tomorrow if we don't get through it. My plan is I also have 93 ready to go, the notes and all that kind of thing. So we'll get through what we can get through today. All right, lesson 91 takes place on page 594, Introduction to Trigonomic Identities. This may be, and I hate to say this, one of the more complex type of things that we do because several of us already kind of struggle with our trigonomic functions. So let's go ahead and get somewhat of a review over that. What is sine? What is sine? Darian. Opposite over hypotenuse. Very good. So it's based upon a right triangle. And when we're talking about opposite, we mean opposite of the angle that we're looking at from, right? So it's going to be opposite one of the two acute angles. You said hypotenuse. Does the hypotenuse ever move around? No, the hypotenuse is what? The side opposite the right angle. All right, and that's really a better definition than simply it's the longest side of a right triangle. That is true, but we'll always be able to identify it given a right angle. What is cosine? Adjacent over hypotenuse. Adjacent is one of those terms that people tend to struggle with the most, is understanding where adjacent is. I usually describe it as this: it's not hypotenuse and it's not opposite, right? And there's only three sides of a triangle, so it's going to be the third thing that's that's left, right? Process of elimination, we can find adjacent. All right, what is tangent? Opposite over adjacent. Okay. All right, so let's see. Let's come back over here. Come on. Okay. Introduction to trigonomic identities. It has already been shown in previous lessons that tan theta is sine over cosine. One of the things I want you to understand is that whenever we're talking about a coordinate plane, right? Let's say we've got our coordinate plane down here, and we're looking at a right triangle, right, where I have this and this, okay? Cosine is going to be equal to that x-axis, right? Because it's adjacent, it's always going to be the side that's on the x-axis. Does that make sense? Right, so cosine equals x, right? And sine is going to equal y, because if you look at from here, y is always that opposite, right? So even if I'm over here, okay, I'm still on the y-axis. I'm still representing the y-axis with sine. Does that make sense? All right, so hopefully it will make some sense to us as we look at this, that tangent is sine y over cosine x. Okay, do we see that? Now it says that it's been previously stated. I don't know that it necessarily has been previously stated or that they made a real strong point of it, but hopefully we can see now that tangent is equal to sine over cosine. Can we see that here? Okay, good. So this is an example of a trigonomic identity, meaning this is that I can substitute sine over cosine in for tangent. Or if I saw that I have sine over cosine as a function, I could substitute tangent in for that, because essentially what an identity means is two things that, it's essentially going to cancel out. They equal each other. I can substitute one in for the other. Okay? So hopefully we can follow that. Trigonomic identities are expressions that relate any two trigonomic functions. Several trig identities will be discussed later in this lesson, but two of the most commonly used trigonomic identities are two that relate sine and cosine to each other. For instance, these are probably the two most commonly used trigonomic identities. Okay? And so this first one we've already discussed. Okay? Tangent theta equals sine theta over cosine theta. The second most used, okay, is sine squared plus cosine squared equals 1. Okay? Can you tell me kind of what that looks like? What does this look like as we think about, when we're talking about trigonometry, we're typically talking about a right triangle, correct? Okay? What does this formula look like? Exactly right. It looks kind of like the Pythagorean theorem. Okay, so that's what I want you to think about whenever we consider sine squared plus x, cosine squared equals 1. But beyond that, we have a whole list of them on how we can relate certain functions in terms of other functions. So let's go ahead and turn over to page, it'll be page 596 in your book. Okay, as we're talking about trigonomic identities, things that we can substitute out, trigonomic functions that we can substitute out for other trigonomic functions. So you'll see now, the reason I left this blank is kind of twofold. One, it's really hard to type into this particular document. All right, so not merely out of laziness, but it is pretty hard. All right, so let's start off with sine theta, okay, or sine. We want to be able to write that in terms of sine. Well, sine in terms of sine is sine, right? It's just sine. Okay, so in terms of a chart, it is what it is, right? It's like saying 1 equals 1. There's no need to change it. All right, but if we want to write this in terms of cosine, you guys have the chart there. What does that actually look like if we were to substitute sine in for something that doesn't include sine but includes cosine? Cosine squared theta, okay? And what if we wanted to write, instead of sine, we wanted to write it in terms of tangent? Okay, tangent theta over the square root of, give me that again? Okay. All right. So the handy thing about this is that the video and all of this stuff gets sent back out to you later on, right? So that you can look at it. And you don't simply have to go back to page 596 to kind of find all of this stuff. All right. All right. Let's go down the chart a little bit to cosine theta. Okay. Now the easiest thing to go ahead and fill in is cosine in terms of cosine theta. Nailed it. All right. So let's go ahead and fill that in right there. Right? Cosine theta equals cosine theta, and in terms of filling in, just getting as much of this in as we can, tangent theta is going to be tangent theta, right? Those are fairly easy, okay? All right, so let's go cosine theta in terms of sine theta. Okay, do you notice, in just in the terms of trying to find things that are going to help us out later on. Okay, look at the relationship of sine theta to cosine theta, as in cosine theta to sine. Right? Do you see the similarity? Right? To switch them back and forth, all I really have to do is I'm going to keep that square root. I'm just swapping cosine out and sine. Right? This is not impossible to kind of figure out. Right? Okay, we're going to see that again and again. What about cosine in terms of tangent? Okay, so this looks a lot like sine in terms of tangent, right? The only difference is that instead of tangent theta on top, we have just 1, correct? That work? Okay, hopefully we see that. Now let's look at, the really difficult ones are tangent theta in terms of other things, okay? But keep in mind that tangent theta is sine theta over cosine theta. So help me out here. What is tangent theta in terms of sine? Okay, sine theta over the square root of 1 minus cosine minus sine theta, sine squared theta. Okay, so here's what's kind of interesting about this, is that because sine, okay, because tangent is sine over cosine, correct? But because in here we want everything in terms of sine. So notice that because tangent is sine over cosine, that we put sine on top, but look at this down here. 1 minus sine squared theta. Do we see that anywhere else? Right up here, right? So this is still the equivalent to sine over cosine. All I did was I substituted out the cosine with the sine form of cosine. Does that like blow your mind? Is that too complex? Can we see it though? All right, all we did, all right, because tangent is sine over cosine, okay, I still have sine over, but I can't put cosine down here because I need everything in terms of sine. So instead of cosine down here, I used an equivalent form of cosine in terms of sine. You got it there? Okay. All right. So over here, all right, we're going to do the same thing, okay? Because I can't write this as sine over cosine, right? And here I need it in terms of cosine. So what am I going to do? I'm going to substitute sine out with sine in terms of cosine. So without even looking at the chart, I can tell you that I'm going to get square root of 1 minus cosine squared theta over cosine theta. Am I right? Boom. Right? Because it makes sense, because tangent is sine over cosine. And then tangent theta is tangent theta. All right? So if you can get this top and middle row, then this bottom row answers itself. You follow me? I know that this is not the easiest stuff in the world. Okay? So that's why these charts are really handy. All right. From there, they're not still out there, are they? Okay, cool. All right, from there, lesson 92, quadrilaterals on the coordinate plane. This is us just putting shapes on a coordinate plane, on a grid. Okay, if the coordinates of a quadrilateral's vertices are given, it's possible to determine the properties of the quadrilateral. Since the length and slope of each side can be found from the coordinates, it's possible to classify any quadrilateral in the coordinate plane. I really feel like this is redundant in review because we've done this. We've seen this on assignments where they gave me a quadrilateral, they put it on a coordinate plane. We had to determine, is it a parallelogram, is it a rectangle, is it a rhombus, is it a square, and how do we prove that, right? We've done that before, right? I feel like we have. I feel like that's a review. So I don't know that there's not really a lot here that you need to see. In fact, no, we're done. We're done there. So let's go on and let's try to work out some questions together. All right. 91, 92. All right, question number 1 says, find sine theta if cosine theta is 0.6, round your answer to the nearest hundredth. All right, so this isn't so much a trigonomic identity as being able to look at something on a graph. If cosine is 0.6, the first thing we need to do is we need to take 0.6 and turn it into a fraction, because trigonomic functions are by their nature ratios, and ratios are fractions. So it's 0.6 as a fraction. Can you put that in your, like, what's 6/10, right? 0.6 is 6/10, right? Right, what's that reduced to? 3/5. Okay, so if we're at cosine, and this is my angle here, where do I put the 3? Cosine is what over what? No. Adjacent over hypotenuse. Where does the 3 would go on the bottom? Where does 5 go? Right here, right? Okay. Now it's asking what is sine, right? So sine is not cosine, right? Sine is opposite over hypotenuse. Well, do I know what opposite is? No, I don't. All right? I've got to find that. How do I find that? Pythagorean theorem, right? So, 3 squared plus b squared equals 5 squared. Now, if you're, granted, sometimes I have to take myself back and say, well, these guys haven't been teaching math for 5 years, so they don't automatically see the same things I see. I see a Pythagorean triple, right? So we have things in math that are like really obvious, like a 3, 4, 5 right triangle, which means if my hypotenuse is 5 and one side is 3, I automatically know that the other side is 4, okay? Or if they're multiples of 3, 4, and 5, right, I just multiply up. So I know that 3 squared is 9. I know that 5 squared is 25. I'm going to subtract 9 from 25. I'm going to get 16. The square root of 16 is 4, right? So I know that this guy right here is 4. So what is sine based upon this? Sine is opposite over hypotenuse. So what am I getting? 4/5. All right? Well, what is 4/5 as a decimal? What does 4/5 equal? Put it in your calculator. 0.8. Okay, 0.8. So our answer here is sine theta equals 0.8. All right? So don't get confused by the decimal. Turn that decimal into a fraction, put that fraction in my triangle, right? Solve for the missing side, then use my new trig function, get my new ratio, plug that ratio in, get my new decimal. I know that seems like a lot of steps, but it's really, we're not talking about anything groundbreaking here, okay? Okay, so that's number one. Come on, there we go. All right, number two. Okay, in parallelogram QRST, it's got vertices at 0, 0, 4, 7, SX, and 9, 0. What are the coordinates of S? Give me a second here, and I'll try to pull up a coordinate grid. Let's see. Give us something that we can draw on. Nope, I just want one great big coordinate grid. We're going to pause this video. All right, from here, let's see, you guys have the document in front of you. I'm going to pull it up here in front of me. Let's see, we're at 0, 0, right? 0, 0. Okay. Next one is what, 4, 7? 1, 2, 3, 4, 7. Okay. Let's see, what do we got? We got x, y, which we don't know what that is, and then we've got 9, 0. So we want a parallelogram. It looks like we got here, and if it's a parallelogram, that means it's going to go straight across out this way. Now, we've run out of coordinate grid space, but it doesn't mean that we can't find the solution, right? All right, we know, and because we've seen a question like this before, if this is 4, 7, what's the y coordinate of the unknown going to be? 7, right? Because my y coordinate up here is 7, and it's a parallelogram, so it's going to stay on that horizontal line, correct? All right. Now, over here, we've got 9, 0. All right. So if I want to find the x coordinate, right, I'm going to look at, this went 4 to the right, you know, from this point right here, and then it went, you know, another 5 over, correct? So we're going to treat this 9, 0 just like we would from this point on. So we're going to go 4 to the right, 7 up, right? So what's 4 to the right from 9? 13. Right? That's how we get 13, 7. Does that make sense? Right? It's a parallelogram, so it's got to have the same slope. So what you might look at with this is rise over run. From 0, 0, the rise is 7. The run is 4. So we're going to have the same rise. We're going to have the same rise, which is 7, and we're going to have the same run, which is 4. So 0 plus 7 is 7. 9 plus 4 is 13. Does that help? No? Okay. Cool. Did I hit record again? Hopefully I did. Okay. Let's see. Let's get back over here. All right. Finally, we're getting back to some of the trigonomic identity stuff with this, but not really. We won't really see it too much until number 4. Number 4, cosine theta of sine theta is 0.8. All right. So what do I want to do with that 0.8 first? Fraction, which is, as we've seen back, it's 4/5, right? Okay. So we know that 0.8 equals 4/5. All right. If this is my angle, where do I put the 4? What's that? Opposite, right? We put it here, right? Where do I put the 5? Adjacent, because sine is opposite over adjacent. We call it, so it's hypotenuse, so it goes here, right? Now, again, we should see that if we're looking for cosine, right, we need this guy right here. What do we know that's going to be? 3. We should know it's going to be 3. If we didn't know that was going to be 3, could we do 4 squared plus b squared equals 5 squared? right? We'd get 25 on one end, we'd get 16 on the other, we'd subtract 16, we'd get 9, we'd find the square root of 9 was 3. All right, but because we're looking for cosine, cosine in this case is what, 3/5? What's 3/5? 0.6. Okay, 0.6 is my cosine. Okay? All right. Now, on number 4, as complicated as it looks, it's really just going back to our chart, right? Okay? Express sine in terms of tangent. Okay, well, go back to your chart. What was sine in terms of tangent? So you're going to look at sine on the left, and you're going to follow it all the way to in terms of tangent, which is what? B. Tangent theta over square root of 1 plus tangent squared theta. Okay? So that was just looking at the chart. Because the trigonomic identities are what they are. They're not going to change at all. Yeah, Darian? Depends upon how the question is worded. If it's this question, I will forewarn you. Okay, you will see that on a review, and you will know what you need to memorize. Okay. For some questions later on, I might give you like a trigonomic identity cheat sheet, but that's more of like an algebra 3 situation than it is a geometry situation. Okay. So this being lesson 92, you wouldn't see a test involving trigonomic identities until probably a couple of tests from now. It's not going to be on this next test, okay, if at all. But if I gave you a cheat sheet, it's just going to be exactly what it is. So at that point, it's almost pointless, you know. I mean, it's not even a good test question because I would just be handing you the answer. All right, question number 5. We've seen stuff like this. Show that this is a square. How do I show that that's a square? What does it have to be first? It has to be a rhombus, and then it has to be a rectangle. What do I know about a rhombus? What am I looking for in proving that it's a rhombus, Matt? You're right, but what is it about a rhombus that I need to show that it is? What are the properties of a rhombus? What did you say, Erica? The sides are equal. All right, so side length, right? If I can prove boom, 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 I proved it's a rhombus, right? Okay. All right, so how would I prove that those sides are equal? I'm going to need help later, but there's 2 different ways, right? There's 2 different ways to find distance, right? Essentially, we're talking about distance. What are my 2 ways for finding distance, Brady?
I was just going to say
Yeah, that's absolutely right. You could use the Pythagorean theorem. So I can create a triangle here where this line right here is the hypotenuse. I'm going up 1, 2, 3, 4, 5, 6 over 3, right? Where that's that, right? Now, what I can do is I can 1, 2, 3, 4, 5, 6, 1, 2, 3. Okay. Let's see, 1, 2, 3, 4, 5, 6, 6, 3. 1, 2, 3, 4, 5, 6, 6, 3. Right? So really, if I solve the Pythagorean theorem once, have I solved it all 4 times? Okay. But it doesn't hurt to show that works. 6 squared plus 3 squared equals c squared. We got 3 plus 9. We got 45. We got square root of 45. You know, you could break that down. 45 is what, 5 and 9, 3 and 3. So really what we're saying is 3 radical 5, right? 3 radical 5, 3 radical 5, 3 radical 5, 3 radical 5. So have we proved it's a rhombus? Sure did. Okay. Now, I went through that really quick. You would want to double check and make sure that those links are what I said those links are. Okay, I'm trying to, we got 3 minutes type of thing, try to get through this. Okay, the next thing is what? What's that? Slopes, right? I need slopes. All right, so we need to look at this. This is up 6 over 3, right? Up 6 over 3, rise over run. So what's 6/3? What's that a slope of here? 2. Okay? Let's look at this one. This one goes up 6 over 3. So what's that slope? 2. I always do that in here. I always assume that we're out at like 36. All right, here I'm going down 3, right? Because it's rise over run over 6. So that's -3 over 6. -3, down 3, right? So what's the slope there? -1/2. What do you notice about 2 here and -1/2 here? What relationship do those two slopes have? Opposite reciprocal. All right, opposite reciprocal slopes form what kind of angles? Perpendicular right angles. All right, so we could see that those two are perpendicular. But also, do I see a perpendicular relationship? So I see a perpendicular relationship between AB and BC. Do I see a perpendicular relationship between anything else? What else?
AB and AD.
No, not yet, because I haven't found the slope of AD yet. But if I found the slope of, okay, BC and CD, I can tell that those are opposite reciprocals, because this one's 2, that one's -1/2. So they're opposite reciprocals, so they meet at right angles. All right, this one is going down 3 over 6. So what's the slope there? -1/2. So these meet at right angles, and these meet at right angles. So do you see how, go ahead.
Do you really have to like do all that work? Because isn't it like if one of the angles is right, it'll force all the other ones?
That is true if it's a parallelogram, right? And if we're saying that it's a rhombus is a parallelogram. So yeah, you're absolutely right that if it's a parallelogram and it has one right angle, then it is by nature, well, if it's a rhombus and it has one right angle, then it's a square. Okay? So yeah, you would be right in saying that. That's a very astute observation of Brady Reynolds. Everybody tip their hat. You know, we're going to do like the old-timey, here, here, you know, like really commending there. Okay. Let's see. So you'll see some of this down here where they're giving it as a multiple choice option. 3 radical 5, 3 radical 5, 3 radical 5, 3 radical 5. So all are congruent. So all sides are congruent. Slope AB is 2. Slope BC is -1/2. Slope CD is 2. Slope AD is -1/2. Since the slopes are adjacent sides, since slopes of adjacent sides have products that equal -1, the sides are perpendicular. That is the answer. That's not necessarily how we're used to wording it. You know, is multiplying slopes and getting -1. What we're used to seeing is, you know, are they opposite reciprocals? But if I did multiply 2 times -1/2, I would get -1, which shows me that they are perpendicular. So A is my answer out of that. Okay? All right. Can't wait till I just hook the smartboard up to my brain and it just does what I want it to do. We're getting there, folks. We're getting there. Which of the following is the most descriptive name? Oh, goodness. Can I just tell you it's going to be a square? Move on with life. Because we'd have to go through and do pretty much exactly what we did with question number 5, except more work. We'd actually plot all 4 points, then find their distances, right, and then find their angles, right? That's what we would need to do with question number 6. All right, do you trust me? I feel like Aladdin. Jasmine, do you trust me? Brady said yes, so we're going to move on. Okay, that is a square, but for all the same reasons that we found in question number 5. And question number 11. All right, so let's, I don't even have enough graph to look at this. It says, is ABC a trapezoid? Explain your answer. This is a trapezoid because exactly one pair of opposite sides are parallel. You need to know some things about trapezoids. Okay, we should see 2 sides are or one pair of sides are parallel, but the other 2 are not. Okay, And that's going to be a trapezoid, so our answer there would be C. On our next question down, number 8, find sine theta of cosine theta is 0.34. Okay, so this goes back to what we saw in question number 1, like I'm going to say question number 3, that same thing. So this is bringing me to making a triangle. Okay, but what do I have to do with that 0.34 first? Fraction. So that's 34 hundredths. 34 over 100. Divide that by 2. What's that come out to? Was that 17 over 50? There is, go ahead. 34 divided by, what's 0.34? What is it, 17 over 50? Okay, so you could look at it, let's say that this is our angle here. You could say, if it's cosine, we're going to do 17 over 50, right? Then we'd have to find this other guy, right? And so we would do 17 squared plus b squared equals 50 squared. We'd get some pretty big numbers there. But there is another way to do this that's going to use one of the principles that we learned fairly early on. And that is that sine squared theta plus cosine squared theta equals 1. Did we see this at the beginning? Yes. Okay. So let's look at it like this. Sine squared theta plus cosine. Well, cosine there is 0.34. So 0.34 squared equals 1. All right, so what's 0.34 squared? Something like 0.1156. 0.1156 equals 1. If I want to find sine, what am I going to do with 0.1156? Subtract it from 1, right? So sine squared theta, what's 1 minus 0.1156? 0.8844, but I don't want sine squared theta, I want sine theta. So what do I need to do with 0.8844? Square root. Okay, so sine theta equals what? 0.94, right? Okay, so 0.94. I'm not saying that you necessarily want to do that. Could we have found that answer using the Pythagorean theorem? I dare say yes. Okay. All right, but this way I don't actually have to draw the triangle in order to see the relationships. For instance, find cosine theta if sine theta equals 0.56. What I'm going to do is 0.56 squared plus cosine squared theta equals 1, right? Find out what 0.56 squared is, subtract it from 1, then square root that answer. Okay? All right. So, well, let's keep working that out. Okay, just so we get the practice of trying a different way. Okay, what's 0.56 squared? 0.31. So 0.31 is what you're saying there, right? Okay. So 0.31 plus cosine squared theta. What am I going to do? Subtract. Okay. So cosine squared theta. What's 1 minus 0.31? Why am I getting something different here? Let's see. What do you say it was? What was point 0.001? I was just thinking, I was like, this is not looking right at all. 1 minus 0.31. 0.69. Okay, I think at some point, did you guys shorten this 0.31 down? No? It wasn't like 0.3136? Okay, all right. That's what I'm saying. It's like, man, this is not what I've got. 0.3136. So let's be a little bit more specific here. What is 1 minus 0.3136? 0.6864. You see the difference there. What did you guys have, like 0.68 earlier? But you can see that if we took that further out, we'd actually get 0.69. Let's square root that. 0.83. Okay? So I'm going to tell you on these decimals that you're going to get for these, take them to 4 decimal places. Okay? That's going to, I mean, granted they do go further out than that, but don't shorten it to just 2. We need more information than that. Okay? What time do we get out of here? 46? 48? We got like 2 minutes. Okay?
Okay. 48 minutes and counting.
I didn't ask you to do that. It's cool. My phone's going to go off in like 47 minutes and 50 seconds for no reason at all. Okay, so let's see. Number 10 is going to do this same thing again, right? I don't know what you prefer. Do you guys prefer to use the Pythagorean theorem method, or does this work out for you? What's that? Okay, but you do still, for one, I can see where some of you are going to struggle with using the Pythagorean theorem is if they tell you cosine theta is 0.57, you have to do a handful of things, right? You got to actually do more work because you're taking 0.57 and you have to get a fraction. What is, so you're getting 57 over 100 there, right? That's not going to reduce, right? And then you have to put that 57, you got to put the 100 in the right spot, and then you got to find the other guy, right? So then you have to draw a picture, you have to put the elements in the right places in that picture, then you have to do the Pythagorean theorem, make sure you go through all that process, then you've got to get that final fraction into a decimal form. So you should get the same answer, but you do have a little bit more room for error, okay? So I don't care if you use your trig identity for this, or if you use Pythagorean theorem, so long as you get the right answer. Not very many math teachers will tell you that. So I will finish up this lesson with the other class. Both videos will go up, okay? I am going to give you guys in class tomorrow to work on the assignment because there will be a sub tomorrow, okay?